Okay, we're going to talk about, shh. Listen, I'm going through this. You're responsible whether I get through it or not. Okay? I will get through it if you're quiet, behave. Otherwise, you're still responsible for it. Is that clear? How difficult was the test on Monday? Was it difficult or not difficult?
On a scale of easy to stupid.
Okay, that is because the majority of it, and I'm gonna be frank, the majority of it is because there's a lot of goofing off, not much note taking, Mr. Paulson. Guys, I go over this. What was on the test? There was nothing new, absolutely nothing new that I had not gone over. No, wrong. Guys, the issue, if you did not do on the test, is because you're not paying attention. You are not going over the notes and asking yourselves questions, make sure you can understand it. And if you don't, you aren't coming to see me. Very few people came to see me before the test. Okay? You have to physically work the problems, make sure you understand it, and that means take notes in class. I'm being very clear about that. These are questions that accurately represent the information that you should know and understand. This is not about equation, chugging numbers through equations. It is about understanding the content. You will have another assessment next week before the seniors go. And then there'll be a final. All the material I'm going over is going to be on both of those, the assessment and the final. Yes, ma'am.
Have you thought about what day of the week it's going to be yet?
What?
The assessment.
I think if I understand correctly, it's going to be on Tuesday. Okay. It's a problem set. It's going to be a problem set where you guys work together. It's not going to kill you. Okay. Project day tomorrow. Okay. But that means, listen, I give you project days so you can work on your projects. If you do not come to class able to work on your project, you will be working on other things for my class. So project day is not a blow-off day. Is that a feeling that people think that the project day is a blow-off day? I hope not, because sometimes there are people who are just sort of twiddling thumbs and saying, I don't know what to do. That's not appropriate. You've got a lot to do. All right, we're going to talk about work. And you are all going to say to me, Mr. A, I know what work is, because we work all the time. You work very hard, don't you? Huh?
Push something and it's not moving, it's not working.
What?
You push something and it's not moving, it's not working.
Right, where did you learn that? In middle school?
8th grade.
All right, great.
Is that in Chile?
So I'm glad. Was that in Brazil?
Yeah.
Okay, did anyone else learn that in middle school here?
We learned it in 5th grade.
You learned it? Okay.
Oh, yeah.
So, okay, now I can continue. So work is equal to force times the distance. Remember, if I don't get through it, you're still responsible for it. Okay, force is equal to distance. I'm going to move on. I ended at a certain point at the other classes. Okay. If I don't get to that point, I'm moving on to the next part. I'm skipping it. And you guys need to go figure it out. Force times the distance that we move an object, the force parallel to that distance. Okay? So if I have a crate or some object, and I'm sliding it or moving it along a surface, okay, with some sort of force, and I'm going to move it, have moved it some distance d, the amount of work is equal to the amount of force times the distance, okay, where force is in newtons, distance is in meters, and when I multiply them, I'm going to get work in joules, okay? So if force pull is 100 newtons, and I move it 5 meters, how many joules of work have I accomplished? 500 joules. Okay, good. Now, there is a misconception about work. I'm going to give you an example where I have my crate again, right? The Tasmanian crate. Right, and we're going to pull this crate up with a rope. okay? And it's lifting it off of the ground, and it's going to have a velocity upwards, constant velocity. Let's draw the free body diagram of that crate. What are my forces on that crate? The force of gravity, Fg, and what is the other force or forces on this crate? Tension, or the force pull up, right?
Yeah.
From a crane that is pulling up this crate. Okay, now, how do I create the equation for the sum of the forces in the y? Fp plus Fg equals what?
Zero.
Well, wait a minute. The what?
Net force.
The net force. The net force. Now that net force is only going to be 0, Mr. Brylan, when which two things are possibly occurring? One of them is when it's not moving. Why is the net force? If the net force is 0, what part of the net force is 0? Is it my mass is 0 or my acceleration is 0? Acceleration. So acceleration is 0 when either the object is not moving or what? Constant velocity. My velocity is constant. So in this case, even though I have this equaling 0, because I told you I have a constant velocity, okay? It's 0, but am I doing work on the box? Why am I doing work on the box? Because I'm lifting it, right? So I am applying a force. The crane itself is applying a force. So the work of the crane is equal to force pull times the distance that I travel. Let's say the distance I travel is 10 meters. So force pull times the distance. For force pull, and let's say force pull is, let's say F of G is negative 100 newtons. What's my force pull going to equal?
Like, if it's going up, you mean.
This is an important question. Tucker,
Wait, I just have another question.
hold that thought.
What's your question?
Okay. The crate is moving up at a constant velocity. My force of gravity, the weight of the box is 100 newtons, which is negative. What, if that's the case, what is the value of Fp?
Over 100, greater than 100.
Okay, so you're saying, let's just say over 100, it's 101. Let's put it into our equation. 101 plus a negative 100, does that equal 0?
Wait, you're losing. It's 100 to less equals.
No, it can't.
Wait, is this for acceleration or while you move?
Moving work.
The problem is, as I stated, the crate, hold on. The crate is moving up because the crane is pulling it up
Velocity
at
is
a
the distance
con-
over time.
at a constant velocity. I said it's a constant velocity. We've said if it's constant velocity, what's the net force? 0.
So there's no work.
Wait a minute.
It's no work.
This is okay. This is the misconception I want to get through. Hold on. I asked before I even get to that point, if the force of gravity is 100 newtons, what must the pull force be if I have a constant velocity? 100 newtons. Do you see why? Because if it was 101, I'd have a net force of 1 newton. If I have any net force, what's the description of the motion of the object? It's accelerating. But I've already stated because I'm constant velocity, what's my acceleration? 0. The only way to make that 0 is to make Fp equal to...
How is it going up then?
But that's the point.
Velocity.
I have... Okay. What you're saying, well, how did I get from not moving to moving in a constant velocity without any force?
Yeah.
That's the thing. That's the misconception. Envision it as a movie. A very short, boring movie. The cup... You're welcome to go to Mr. Gunnar's office and be bored there. I'm going to take the cup, I'm going to lift it up. Okay? Right now, the net force is 0. In order for me to even move it up, I have to change the velocity, don't I? Because what's the velocity now? I've got to get it from here to a constant velocity. So at that time between here and here, I have accelerated it. So at a certain point of time, I did have more force. But once I had more force, I leveled it out, and now my forces are equal.
Okay.
Do you guys see that misconception? You see that? It's exactly right. And it's about the clipping of the film, right? So if I'm moving at a constant velocity, I can still have a balanced force. If I had, in a prior time, applied an unequal force to get it to move. Got it? Okay. So now we know that the forces both have to be equal and opposite of 100 newtons. Now, Avery, your statement was, well, wait a minute, we're not doing any work. We're not doing any net work, okay? Because what's happening is that the crane is applying a force and moving it vertically 10 meters. So the crane is applying a force of 100 newtons, positive, times a positive 10 meters, okay? So it is doing how much work? 1,000 what? 1,000 joules of work. But if the rope wasn't there, what would happen? It would fall because of what? What is pulling it down? Gravity, right? So we have the work of gravity is also doing work. Okay? It's pulling negative 100 newtons, but the object is going the other direction, so it's negative 10 meters, and therefore we're getting a positive 1,000 joules. Okay? And it's actually doing it the opposite way. So it's actually doing, I'll do it positive, right? So we're doing work in the opposite direction, so the net work ends up being 0. Okay? So they're doing work on either side.
So really, what we're saying is that both sides are doing work. However, in like when it all gets down to it, there's actually 0 work going on because they balance each other.
Because they balance each other out, right? But it's a question of how much work is one thing doing on the object versus the other thing doing on the object, and there's a total network. Now, okay.
But isn't in this case the work of the gravity being the normal force?
The normal force comes from the floor pushing up on the object. There's no floor pushing up on the object. So we just have gravity pulling down.
But if they're weighing, if it weighs each other out, then is there really work? That's the thing.
There is, right. There's no net work on the object if I'm moving it at a constant velocity, right? But the crane has to do work to overcome the work that gravity is trying to do on it. Okay. I had something else I was going to say. I lost it.
Can you turn it over for
Yeah. Yes, ma'am.
So this is going back to when we were talking about constant velocity. When we're doing like the math and the equations for it, is it okay if we don't is there a way to specify the difference like that we know that it's constant velocity versus and it's 0 versus it's not moving and it's 0? Or like when we're doing math, is it okay just write net force equals 0?
Net force. You say net force equals net force equals 0. You'll either have been told why or you.
Because it'll give us that it's constant velocity.
Or yeah, I'll tell you it's a constant velocity or constant acceleration. Yeah. Yes, sir.
So the work of gravity is force of gravity times the distance.
Times the distance, right? So, but this is what I was going to say. The issue though is the time that my net force isn't 0. So my net work isn't 0, is when my net force isn't 0. When I'm doing more work to accelerate the object. But once it's in constant velocity, my net work is 0. Yes, sir.
I'm getting sort of hung up on the whole concept of distance in this formula.
Okay, distance is how far I'm going to move the object due to a force.
So it's how far you would have moved the object if there was nothing else pushing you?
No. It's how far I move the object because I'm pushing on it.
It's not moving at all.
It is moving it all. It is.
It is moving?
Velocity constant, upward. I said it's moving at a constant velocity, move 10 meters upward.
But you said the force of gravity balances it out.
Yeah.
So
The forces are balanced. This is what I just had this conversation with Enrico. You're saying, well, if my forces are balanced, how could I be moving?
Right.
That's exactly his question. Where were you when he asked that question?
I was listening.
What was my answer then?
I didn't.
I don't think you listened.
There's like an initial force that pulls it up, and then it goes back. I didn't understand.
But no, go ahead. Enrico, explain it to him.
I'm still confused. But like it's like initial force where you pull, and that's above like 100. But then you like go back to 100 and say like that.
So the issue is this is a movie clip. Okay, we're in a movie, and I'm gonna look at a portion of the movie, not the entire movie. The entire movie begins, the beginning of the movie is when we learn about the cup and its existence. It's existing there. Poof. Then the big bad crane comes in and grabs the cup and pulls up. Now, in order for it to go from zero velocity to some velocity, you have to change its velocity. A change of velocity over time is acceleration. So now if I have a net acceleration, it means I had a net force up to get it to start moving. If I keep applying a net force, the cup is going to continue to accelerate. The velocity is going to continue to increase. But I said, wait a minute. I'm just going to get it to a point where it goes to a certain velocity. I'm then going to let it be at a constant velocity. And now my force up equals my force down, but I've already accelerated it.
It's kind of like with an airplane. Like when it takes off, but then suddenly it gets like where it's gonna be. You know?
I know exactly where you're going, but that might confuse other people. But your analogy in your head, I know, yes, but not exactly. The issue is that you're going to accelerate up, and you're going to, and to her point, you're leveling off. Your velocity is going to increase, and your velocity is going to level off. Okay, but in order to level off, all I have to do, if I'm leveling off and my velocity doesn't change, no change in velocity over time means what? I have no acceleration. Think about driving a car. In order to accelerate from zero, I've got to hit the gas. And I got to push it to the pedal. When you get to your current speed, what do? You let back off on the gas a little bit. And then you're only getting enough force to overcome friction. And you're going at a constant velocity. Your forces are balanced. Okay? All right.
Wait, Mr. For the word of gravity, it says negative 100 meters plus 10 meters equals negative.
I'm sorry. Excuse me. You're right. Times positive 10 meters.
Equals negative 100.
Yeah, 1,000. 1,000 joules. Okay? All right. So, does everyone sort of get the concept of work? Right? I'm doing work on an object because I am making that object move because of a force I have on it. Clear? Okay. Now, we're going to talk about energy for a second. Energy. There are two basic types of kinematic, meaning motion, energy. Okay? There's, kinematics is not the right word, but there's two basic energies aside from spring and other mechanical energies. Those two are, does anyone remember those two from middle school? Kinetic and potential. Okay, so that is, oops, KE, and this is PE. What is potential energy? Someone talking about what potential energy is. Brylan, wake up. What is potential energy?
Is it like right before it becomes kinetic? It's like how, I don't know how to describe it. It's like, isn't that
Anything that hasn't been
isn't that the
inserted yet.
roller
Wait, say it again, Sean.
Anything that hasn't been inserted yet.
Yeah,
coaster?
it's
Still there.
yeah, it has the potential to do something. Charlie Ray said this morning, I love this one. It's like looming energy, right? It's about to. Someone said Charlie would say.
Like a looming storm.
Yes. So the energy this object has the potential to release some energy. Okay? And does anyone remember the equation for potential energy?
A long time ago, like 4 years ago.
Okay. mgh, where m is my mass, g is the acceleration due to gravity, which is negative 10 meters per second squared. People will use the term g, or the letter g, to represent that one specific acceleration rate. Every other acceleration in a car or something else is always going to be different. But the acceleration rate of gravity is never going to change. Wow. Never, it's not really. I'm sorry?
NGH is only potential.
I can't hear you.
NGH is only potential.
That's what it says right there. P is mgh. So h is what?
Right.
My height. Okay? So if I have an object, Happy Fun Ball, up at the top, don't taunt Happy Fun Ball.
Not taunting your general.
Yeah, is it happy? Is it? Yeah, Happy Fun Ball. See? Don't taunt Happy Fun Ball.
What? Is that like a reference we're supposed to understand?
Yes.
To what?
I think the last week of school, I'm gonna just be playing while y'all are working. I'm gonna be playing clips from '80s movies to get all my references.
Please. 16 candles.
Right now, or ever.
Cannonball run.
Well, it's the end of the year.
Cannonball
Why did you
run.
tell me now?
I always tell you that I
You-
can't understand.
No.
Remember, I'm like, make it bigger, blah, blah, blah. But that says NRG, that's NE.
Energy. It's a short form for
What's that
energy.
one next to potential?
Energy.
NRG.
PE. Potential energy.
Okay, I thought it was some slang. I wrote down NE.
Cannonball run. Energy.
Height. H is height. Okay? So when I look at this, guys, for a second. When I look at work is my force times my distance. Force, how do I break down force? Force is what two things multiplied together. Mass times acceleration times a distance. Well, look at this. Mass times acceleration, distance, distance. Oh, look at that. Energy is work. Work is energy. Potential energy is work to get up to that potential energy. Okay? Do. Weird. Sorry.
What'd you say, G was again?
Huh? G is the acceleration due to gravity, which is negative 10 meters per second squared. Or 9.1. It's fine. Now, shh. Okay. Here's the deal. This object has the potential to fall down.
It may not.
Huh? Okay, we're good. All right. So, the potential energy is equal to my mass. Let's say my mass is 5 kilograms. Let's say my height is 10 meters. What is the potential energy that the ball has?
500.
Okay. It's going to be mass is 5 kilograms, right? PE equals mass times gravity times height. So PE is equal to the mass is 5 kilograms,
Negative 10 meters per second squared.
negative 10 meters per second squared, times a height of, it's going to go down, so negative 10 meters.
500.
So it's going to be 500 joules. Okay? Guys, quiet. You with me?
What?
Negative 10 because it's going to go down. Not 500 joules is the potential energy that it has. Yes.
No.
Yes. Okay, let me move on.
Why is it 10 meters?
Because it's, I said,
Negative 10.
negative 10 because it's going to go down, which is a negative displacement.
Gravity.
What?
That's the force of gravity. Is negative 10.
But it's going to, the displacement is going to create is a downward displacement.
The distance is up also.
It's currently up, but it's going to go down.
No, but if we're on the bottom, it's going up. So why would that not be?
Then if we were in the bottom and going up, gravity. Don't argue. I get it.
Don't get it.
Okay, this is 0 meters, this is 10 meters. To go up, final minus initial, 10 minus 0. To go down, final minus initial, 0 minus 10, negative 10. Right? Now we're clear? Okay. Now, what's good, boy? That's great. So the potential energy is dependent on the height, okay, above the what? The height above what? The ground. Now, where did we hear potential energy? Where did we earlier this year use potential energy and ground before? Electricity. Didn't I draw the same diagram every time? Yeah. Okay. So the potential energy is relative to the ground you're referring to. So this ball has a height above this ground. And therefore it has a potential energy relative to this ground. But if I open the window and drop it out, it's going to have more potential energy relative to the ground down below. You follow me? Okay. So it's all about the change in your height. Okay? So I should actually say mg delta h. All right. So now here's the thing. As this object goes down, what happens to the potential energy?
It decreases.
It decreases. The potential energy decreases because does my mass change? Does gravity change? Because my height changes. You're right. Hold on. You're right. Hold on. So if my height changes, my potential energy decreases. Avery, where does that potential energy go that decreases? But where's it go? Just where's it go? But it goes into kinetic. Okay. So.
Is that where it like equals out? Like as the potential gets lower, the kinetic gets higher.
Okay. So in any.
It's all about.
Okay, here's the scenario. Basic scenario, I've got a ball again, right? Happy Fun Ball. Happy Fun Ball has a velocity. Okay? What's it going to do? What's it going to do? I'm going to get there in a minute. Where's it going to go right now?
It's going to go up the hill.
It's going to go up the hill until what?
Until gravity is too much.
Okay. Okay. So, yeah, and let me, Amr, you're right. Let's talk about it. If I have motion, if my Happy Fun Ball has motion, it has kinetic energy, which is equal to 1/2 mv squared. So that kinetic energy is directly related to the velocity that the object has. As that object travels up, what's going to happen to the velocity of the object?
It's gonna keep increasing.
As it goes up, the velocity is going to increase? It's going to decrease. As it goes up the ramp, the ball's going to decrease, right? The velocity of the ball is going to decrease. You suppose?
I mean, for the first tiny bit of it, there has to be a point in which it suddenly starts decreasing. But like, as soon as you push it, it's like gonna because of acceleration, the velocity's gonna be.
Yes. Again, we're talking about when do I start my movie? When am I clipping into the movie? The ball is already moving at a constant velocity. Yeah. And now if it's going to go up the ramp,
Then it's gonna slow down.
thank you. Yeah. Okay, I got it. So we're going to have a height, and we're going to have a height. My height's doing what as the ball goes up the ramp? Increasing. So what's happening to my potential energy? It's going up. The potential energy is increasing because my height's increasing. What's happening to my velocity? It's decreasing. Okay? So, at any point in time, the ball, let's call this at the ground level, the ball is going to have potential energy and it's going to have kinetic energy. Hold on. I know what you're saying. Hear me out. For a total energy, at a certain point up here, it's also going to have potential energy and kinetic energy. And that's going to equal another total. Different potential, different kinetic. Yes, sir, Amr?
Are potential energy and kinetic energy, do they have an inverse relationship?
I'm going to talk. That's what I'm doing right now. Focus up here. So at the ground level, what is the potential energy that it has? 0. If it's mgh at this level, what's h? What's the value of h? 0. So that's going to go to 0. Plus 1/2 mv squared. So there's going to be all of my energy is equal to my kinetic energy. As it goes up, at this point, mgh and 1/2 mv squared. Let's assume this point is where the ball stops and starts to turn directions. So what's the velocity right at this very top point? 0. So my kinetic energy is 0. So as my kinetic energy goes from some number to 0, my potential energy goes from 0 to some number. It trades off. Yeah. There's momentum in there too. But okay. But here's the thing. Did I tell you the secret to physics?
No.
I never told you the secret to solving all problems in physics.
Follow the equation.
No. This is I'm serious too. If you're stranded on a desert island and you have to solve a physics problem to save your life, and you don't have a physics book, here's how you solve the problem.
Keep a map in your pocket.
I will phone a friend.
There is no phone. It's a deserted island.
Well, then I guess
Why would
it's
physics
acceptable.
be there?
He said it's going to extend my fate. Into the volcano!
Yeah, me too.
Like, take me.
It's time. So the magic solution to everything is that everything the change of everything is zero. That everything adds up to zero. You cannot create or destroy anything.
Yeah, not you can create a
Right.
problem.
So my energy, if I have my energy from kinetic and it rolls up the hill, all of that energy none of that energy can be destroyed or created, so it has to get pushed everywhere. If I have no potential, all of it has to get converted to kinetic. Now, yes, there's some loss to the air resistance, there's some loss to the heat and sound, but
It
if
just comes back on in.
huh?
It just comes like back into the system.
Well, if my boundary layer includes the air around it and the noise around it, then all of that energy is still in the same box. Hasn't gone anywhere. Now, if I focus just on the ball, then energy leaves the ball. But this is exactly the hard point. Like, where do you draw the boundary box? Okay, you guys with me?
Yeah.
Okay. So here's the thing. Energy total at this point is equal to energy total at this point. At the middle point, what's my energy total equal to?
0.
No, it's the same as the other two. Do you see why?
Yeah.
Okay. It's all equal. The energy totals are equal. But in this middle case, I have some potential energy and some kinetic energy.
Maybe.
Maybe,
They're in the
right.
middle.
No, that's exactly right. Someone said equal this morning, and they're not. They're not equal and half. They could be.
Because a slope is different than like a diagonal.
Well, it depends also where am I on this? Am I midway in the height? Don't know. I haven't told you. Right, exactly. Okay. So here's a problem I'm going to give you that you can start working on today, and because we ran late, you have to work on it tonight. Okay? Isn't that fun? Okay. Here's the problem you need to work on today, and then tonight. Okay. Happy Fun Ball is up at the top. Okay. Here's the height. I'm going to call this A. So height at A is equal to 100 meters. Here's point C. The height at C is equal to 0 meters. Okay? Here's point B. The height at B is equal to 34 meters. The velocity at A, the initial velocity at A is 0 meters per second. The mass of the ball is equal to 10 kilograms. Your acceleration rate due to gravity is negative 10 meters per second squared. What I would like you to do is do the following. And you need to do this for a grade now because you're behind. You got to get this caught up.
Great, let's go.
Okay? You're going to have to figure out the total energy. Okay? And remember when I'm coming back. Remember when I wrote this equation right here?
Yeah.
Even though at the top, how much kinetic energy do I have? 0. I still put it there. It's still PE plus KE. It still has kinetic energy even if the value of that kinetic energy is 0. Don't not put the placeholder in even though you think it's 0. You follow me? If you follow this construct, you will never get it wrong. If you try to take shortcuts, that's where you're going to make mistakes. What is the equation for the energy at point A? What's the equation for the energy? PE at A plus KE at A gives me what? Energy total at A. What about C?
PE at C
Plus?
KE at C.
Okay. What about here?
Same thing with these.
PEB plus KEB equals ETB. And you know it, and you can break this down into MGHA plus 1/2 mva squared equals E total A. Now,
mg
the total energy at any point is what? Equal. So you need to figure out the total energy, the potential energy at A, B, and C, the kinetic energy at A, B, and C, the velocity at A, B, and C, and that's it. Cool? That's what you need to do tonight.
Wait, I'm a little a bit confused.
Yes.
So basically, how many answers are you looking for?
You're looking for 3 answers for PE, 3 answers for KE, 3 answers for B. You already know VA. What's VA? 0. Okay?
Can you go back to the other screen?
Huh?
Can you go back to the other screen?
Okay. I'm going to move back to the other screen. Sean, you ready? Okay. This one?
Yeah, what was the half MV for?
Kinetic potential energy equals mgh.
Yeah, I get that.
Kinetic energy equals 1/2 mv squared. Okay? That's what you need to do tonight. Oh, we got 5 more minutes. Oh, you can start to work on it now. You can start working on it now. All right, go work on it now.